Hello everyone, welcome to the Innovation Lab. In this video guys, we're going to start a new video series with much focus on finding affordable innovation for you guys. So in this video, what we're hoping to accomplish here is to know if there's a way we can merge the already existing MPPT solar charge controller technology with the affordability of these constant current and constant voltage DC to DC buck converters that we have out there in the market today. Alright guys, so what we're really hoping to capture here is a DIY alternative, something that you guys can easily implement, and also something that's going to be very affordable and also removes that power limitation that these MPPT solar charge controllers are designed with. But before we get into that, we're going to first of all in this video focus our effort on reviewing these constant current and constant voltage DC to DC buck converter, because when we do that, it kind of shows us the limitations of this converter so we know what to tweak as we go into this hack. All right, my friends, if you're excited by what I'm saying here, then buckle up and let's get started. One of the things I'm really hoping to capture in this video is to take this converter apart, then we place it under our lab microscope so we can really scrutinize and know all the major components that this converter is designed with, so that will tell us how to tweak it in the future. But before we go into that, I want to really explore the performance of this converter as a DIY battery charger, and we're also gonna use it to drive a purely resistive load, and right after that we're gonna use it to drive our power inverter. The power inverter drive test is gonna be for those of us who happen to have battery systems of higher voltage level that their power inverters cannot handle. For example, if you have a 60 volt battery system and you have a 24 volt power inverter, would it make sense to use a buck converter like this to bridge that gap that you have between the voltage level of your battery system and the required input voltage range of your power inverter system? So guys, I've really put in a lot of thought, a lot of effort, a lot of research into this video series, and also getting all the materials that we're going to need, at the same time building our solar panel array, building our test setups. My overall goal is to make sure that we have everything we need to allow us to do a comprehensive deep dive into this hack. Alright, in this video I'm going to try to move things around a little bit to keep the video fun and interesting for you guys. Alright my friends, let's go ahead and build a test setup, and after that we'll jump right into all the fun. All right, so let's go ahead and talk about the specs and features of this DC to DC buck converter. From experience, one of the major drawbacks you have with using modules like this is that the manufacturers never really take the time to prepare product data sheets that will help you to kind of go through the functions of these converters if you're looking at using it for a deeper level design. But I was able to find a vendor on Amazon that provided a little bit more information regarding the specs of the converter and also the features that it has. So this here is the input side of the converter, and the converter is rated for an input voltage range of 20 to 70 volts with a maximum input current of 20 amps. On this side, we have the output of the converter. This converter has an output voltage rating of 2.5 to 58 volts. It has an output current range of 0.1 to 30 amps and a rated output power of 800 watts. All right, let's talk about the actual features that this converter has that makes it a little bit more appealing. First of all, this converter is a constant current and constant voltage DC to DC buck converter. So if you look on the output side, what you see here is the output adjustment potentiometer. And also on the right side, what you see here is the output current limits adjustment potentiometer. So one of the things I like is how they oriented both potentiometers in the same direction. So to increase the output voltage, you go in a counterclockwise direction. The same thing applies to the output current potentiometer. To increase the output current, or if you're using this to recharge your battery system, to increase the charging current you're delivering to your battery, you go in a counterclockwise direction as well. And the opposite is also true. Yeah, so this is quite impressive. I like the design of the converter. So one of the other cool features that they added here is the output enable switch. So, and you can just get one of these sockets, just get a regular toggle switch. Any toggle switch will work with this. And this allows you really to control the output. So in my opinion, the output enable switch is actually a very cool feature because what it does is to give you a little bit more flexibility in designing your system. So you can have your output voltage configured, you can have your output current limit set, and all you now have to do is essentially to use the toggle switch to talk to the converter and tell it when to give you output and when to turn off the output. So I think this makes your design a little bit more convenient. And honestly speaking, I find it to be an awesome feature. All right, so from the same vendor that I found on Amazon, there was a stated converter efficiency of 93 to 97%. So what I would say is that I have found that to be true actually based on all the tests that I've conducted, and you guys are going to see all of that in this video. You will get to see that the efficiency of this converter, I'm actually averaging around 97 to 98%. Which is quite impressive. Again, what I found from the same vendor is that this converter design promises an input reverse polarity protection. That feature is something I have not tested and I wasn't planning to test it in this video. Maybe I'll get to that in future videos. So with all of that said, there are some missing core specs that I always consider. Specs like input under voltage lockout, output over current protection, input over voltage protection, and many others. And if this is something that you guys have come across and tested, please feel free to interact with the video and share your findings with us. Alright guys, our test setup is complete. And if you have been following my channel, all my projects and all the testing that I conduct at the Innovation Lab, you will know that I like to keep my test setups nice and neat and clean. And the reason why I kind of go the extra mile in maintaining all that cleanliness is to make sure that when you're dealing with electricity, especially when you're testing power systems and power supplies, you want to make sure that everything is nice and neat and color coded. So in a nutshell guys, I go the extra mile just for electrical safety. If you're playing with electricity, you want to be respectful. That way you're not going to have any issues and you're not going to miss anything. All right, so let's go ahead and take a closer look at what we have on our test setup. So right here in the middle is the constant current and constant voltage DC to DC buck converter that we're going to be testing in this video. And to the left of it, at the input side, we have our 60 volts, I want to say up to 3,500 watts server power supply system that is going to be feeding this buck converter system. So this converter is only rated for 800 watts. So when we factor in the input to output efficiency of the converter, I can say that we're not going to pull more than 900 to 1000 watts coming into the converter. That means that our server power supply system here should be able to comfortably provide all the power that we're going to need out of this DC to DC buck converter. All right, so we have our current clamp here to measure the input current. We have the first DMM here to measure the input voltage. As you guys can see, we have 61.3 volts coming in. On the output side, we have our Fluke digital multimeter here. So first of all, we're going to use this digital multimeter to set the output voltage that's going to come out of this converter to match the recommended charging voltage of our lithium iron phosphate battery system here. And here is another current probe on the output side. So we're going to use this to keep an eye on the charging current that we're going to deliver to our battery system. There is a reason why I have all these meters here and current probes keeping an eye on everything. So the safety thing about battery charging, and the reason why I always recommend that you guys use a constant current and constant voltage DC to DC buck converter or boost converter as your battery charging systems or DIY battery charging systems, is that these guys allow you to vary the output voltage to the desired voltage level, at the same time allows you to slowly adjust to whatever is the charging current that your battery manufacturer specifies for that battery system. So our goal for this test is to set a charging current of about 30 amps because that is really what this converter is rated for. Alright, so for us to be able to use this buck converter as a DIY battery charging system, the first thing that we have to do after connecting the input power is to adjust the output voltage of the converter to the recommended charging voltage of your battery system. So in our case here, the recommended charging voltage of this 24 volt lithium iron phosphate battery system is 29.5 volts. And also guys, you have to make sure that this output voltage adjustment is done with the battery system disconnected from the output of the converter. One additional step that I usually take before connecting the battery system is to make sure that the output current limit of the buck converter is set to the lowest point, and how you do that is to adjust the output current limit potentiometer in the clockwise direction until you hear some audible clicks. So when you hear those clicks, that means that you have reached the lowest minimum current level that this converter can deliver. Sometimes you may have to back off a little bit just to make sure that the converter doesn't lose output voltage regulation. Alright, so given that we have completed the initial steps, all that we have left now is to really connect the battery system, and with the battery connected, we're going to slowly increase the charging currents that we're delivering to the battery system. Also, given that this converter has an output current limit of 30 amps, that means that we have to make 30 amps our target for this battery charging test. Alright, so looking at the setup here, we can see that the battery system is charging really well. We're delivering close to 31 amps going to the battery system. So to look at the efficiency of the converter as a battery charger, so what we can see here is an input power of approximately 856.1 watts going to the converter system, an output power of about 846 watts going from the converter to the battery system. So when we do the math at this very moment, what we are seeing is a converter efficiency of 98.8%. This also means that at this very moment, this converter is seeing a total power loss that is less than 2%. And when we do the calculation, we see a power loss of approximately 10 watts. I was also curious to know how this converter will behave when we use it to recharge a battery system of slightly higher voltage. So using the same setup, we were able to use it to recharge our 36 volt nominal lithium iron phosphate battery system. That battery system requires a charging voltage of 43.5 volts. So all we had to do was to increase the output voltage level of the converter. We'll connect the battery system. With that setup, we are seeing an input power of 707 watts, a delivered output power of 681 watts that is going to our battery system. And again, when we do the math, we are seeing an awesome converter efficiency of 93%. So one of the things I forgot to mention was that I also have my oscilloscope connected to the output side of the DC to DC buck converter, and my goal is to really capture the peak-to-peak output ripple as we're going through this exercise. So my scope right now is AC coupled, and let's take a quick look at how much ripple that we're seeing here. So we're seeing a peak-to-peak ripple voltage of approximately, I want to say about 2.42 volts here on channel 1, because that's where we're connected. And I can kind of try to capture the RMS ripple as well. So let me try to do that. I'm going to change that to RMS. Okay, we'll go back. All right, so we're seeing an RMS ripple of 121 millivolts. So we're going to take a mental note of those numbers, and we're going to come back to them and kind of look at the ripple performance of this converter. Alright guys, for this test, so we're going to use this converter to drive a purely resistive load, which is our water heater here. So this is a 48 volt 1000 watt resistive water heater. So we have configured the system. So I believe I set the output voltage to about 43 volts just to be safe. But this goes to a lot of the mistake that I see that a lot of people make. A lot of people have reached out to me in the past, and they mentioned that right after setting the output voltage of their converter, and once they apply load like a resistive load, that output voltage will drop or possibly like crash. This is applicable to buck converters, boost converters, anything with a constant voltage adjustment or current limit adjustment. It's going to happen. So what you're missing is that if you're going to apply a purely resistive load like I have here, you might want to increase the output current limit of the converter to the maximum point, so that way it will only allow that load to take what it needs as long as the converter is rated to handle that load. Or at least if you set it to a higher output current to match what your load should be drawing, then that will prevent your output voltage from crashing too low. And I'm going to demonstrate it right here. Alright, so when you're looking at our test setup here, what you're seeing right now is an output voltage of 23.46 volts going to our load. But the truth is that that is not actually where I set the output voltage of the converter. So you are seeing that voltage level because it dropped when I applied the load. And the reason that happened was what I was explaining earlier. So that happened because I had set the output current limit of the converter low. So now let's see what's going to happen once we increase that output current. Alright, as you guys can see, the output voltage of the converter is rising. So that goes to tell you guys that if you want to have a stable output, well-regulated output voltage coming out of this converter, you need to, especially if you're driving a resistive load, so you need to increase the output current limit of the converter so that when you apply that load, it will be rugged enough to drive that load. Yeah. So in a nutshell, guys, make sure that first of all make sure you understand how much load you're going to be applying to the system, and then make sure that both the output voltage and the output current limit of the converter is set to match that load. So doing that guarantees that the output power handshake between the converter and our load is well balanced. So that also means that the converter will not get overloaded, and also your voltage of your power output will be as stable as it needs to be. And lastly, looking at the what we have on the setup, so we look at the input power versus what is actually coming out of the converter, the output power. So I am seeing an efficiency that is greater than 98%. This is quite impressive, guys. So this converter is performing really well. Of the efficiencies we have measured, apart from the when we try to use it as a solar charger, we are seeing 98% and above, which is quite impressive, which means that we're only losing 2% of the power that is coming into the unit as power losses or heat and all of that. So the final test that we're going to conduct on this converter is for those of us who may have a need to step down a higher input voltage level to a lower input voltage level that they can use to drive the pure sine wave inverters. As you guys can see here, this was a question that a lot of you guys have asked me in the past. So, but the only thing to keep in mind, first of all, is that this is an 800 watt DC to DC converter. So it doesn't really matter how powerful your inverter is. So you can only get what is going to come out of this converter, which is 800 watts. And also, as you guys can see here, I have set the output voltage coming out of the converter to exactly 25 volts, which is within the input voltage range of this power inverter. So the last thing that I would recommend that you guys do is to make sure that you increase the output current limit to the maximum point. So, and you do that by going counterclockwise until you hear clicks on the converter, on the potentiometer. Now you know you are at the maximum point. So that would allow the power inverter to draw as much current as it needs to drive through the load that we're going to put on it. All right, and to be safe, we're going to limit the load that we're going to apply to our inverter system because we need to account for efficiencies. So there's going to be losses here, there's going to be losses here. So essentially my target load on the system is going to be below 650 watts. All right, so let's go ahead and check it out. All right, so we're going to go ahead and turn on the power inverter. All right, as you guys can see, we have a very nice and a very sweet pure sine wave on our scope. So that tells us that the power inverter is on. All right, I'm gonna bring in our load. So first of all, I'm gonna bring in this 300 watt channel, and I'm gonna bring in the next ones, which are just LEDs. And we're gonna end up with another 300 watt channel. All right. I think it presented like a high surge on the converter, but then the system slowly recovered from that. As you guys can see, the converter is driving the entire load. All right, guys, so looking at the setup here and looking at all the measurements that we have collected. So what we saw was that the pure sine wave inverter was applying a load of approximately 635 watts on the system. And looking at the input side of the converter, we saw that the converter was drawing in about approximately 750 watts going into the converter. So when you calculate the efficiency of the system, so you're looking at the overall efficiency of having your power go through the buck converter, now using it to drive your power inverter. So what we are seeing was an overall system efficiency of about 84%. So which means that if you go with a configuration like this, you're going to be losing about 16% of your power to heat and dissipation and all of that. That's going to happen between the buck converter and your pure sine wave inverter. Would I recommend a system like this? So personally, this is not something I would do because losing 16% of my power is not something I would prefer. But if this is the only option that you have to be able to use your system, now you guys have all the facts. Now you know what to expect in terms of power losses and efficiency. So one last thing to really look at here before we go to the deeper dive of this converter is to look at the performance of this cooling bed that I added, as you guys can see here. So what I've done was to replace the original fan that came with the unit, and luckily the fan that I found that I'm using here, which is a bigger fan, comes with the same plug-in that the converter came with. So that was quite a plus there. So as you guys can see, that fan is cooling the system really well. So this converter comes with a temperature sensor, which is kind of tagged to the unit, as you guys can see there. So when the temperature of the heat sink, which is where all the MOSFETs and the diodes are mounted to, when the temperature of that heat sink gets to a set point, it's going to tell the fan to turn on and it will start cooling the unit. And as you guys just saw, that seems to work quite well. Overall, guys, I am very happy with the design of this converter. And one thing I've seen is that even adding this cooling bed makes the converter a lot more efficient because it gives it better cooling. And this is something I designed to have on my website as a product. So that means that I'm not going to be able to share this design file with you guys. But what you guys can do is to go to my website at the Innovation Lab and pre-order this cooling bed. And in the near future, I plan to add an option to where you guys can go to my website and pre-order the complete set, which is going to comprise of the cooling bed and the actual DC to DC buck converter. Also, there may be other options too in the future if we're able to hack this converter or make it perform better as a solar battery charger. So you guys will also have the option to buy the modified version of the converter. Alright guys, I am super excited to get to this point in the video. This is kind of the most fun part of the video for me. So when you have a module like this and you don't have access to the design schematic, which is all good. So where you can start is by looking at the components on the board. So when we understand the design components that they used, so you help point us in the right direction. So guys, the first thing we're going to do is to place the converter on our soldering microscope, and we're going to look at all the components that's mounted on the top side of the board. And after that, we're going to take the converter apart and we're going to look at all the power components that is mounted at the back side of the board on the heatsink of the converter. All right, my friends, let's go check it out. So the first component we see on this board is a TL494 controller. And I am happy to see this because this is a chip that I'm quite familiar with. So my knowledge of this chip is going to be quite helpful to us as we go into this. Also on this board, I've seen a couple PC817s, which is an optocoupler. The next component here is the LM358, which is a dual op amp. I am also very familiar with this component, so that is going to be helpful. And here we have the D5N50, which is an N-channel MOSFET. Also down here we have these two transistors, the B772 and the D882. The B772 is a general purpose PNP transistor, while the D882 is a general purpose NPN transistor. I am also very familiar with these two transistors because they are used in multiple designs as a complementary pair MOSFET driver. And the last component on the top side of the board is the UC3843. This guy is another PWM controller, and I'm thinking here they're using this as a switch mode regulator to provide a kind of auxiliary power to the board. Alright, after that, all we had to do was to take the converter apart, which was quite very easy to do. That was actually one of the things that attracted me to this converter, which is the fact that the converter has a lot of space for you to work with. So with the converter fully disassembled, I was able to pry up those components so we can look at them. The first components we see here is the HY3810. There's two of them used for this design, and these are 100 volts, 180 amps N-channel MOSFETs. My guess here will be that they're using two of them in parallel. For the rectifiers, they used two MBR or 3100 PTs, also I think connected in parallel. So these are 30 amps, 100 volt Schottky barrier rectifiers, and this package that they're using here is a common cathode package. This means that there are two Schottky diodes in each package and overall 4 diodes all connected in parallel. On the input side of the board, we have one more MOSFET, which is the HY3408A. This guy is an 85 volts, 140 amps N-channel MOSFET. Alright guys, so this captures the overview of the major components that we have on this board. So the good thing is that I am quite familiar with all these components. I know their respective theories of operation, and I am quite familiar with the functions that they're supposed to be performing on this board. So my hope is that having all that background knowledge is going to come in handy and help us make good progress. Alright guys, that's it for this video, and as you guys have seen, this converter performed really well. We got really good efficiencies. So we used it to implement multiple functions. We took the converter apart, we looked at all the major components that we're going to be focusing on as we go into this solar innovative journey. So in a nutshell guys, I'm going to go ahead and put this converter back together so we can use it for all the other awesome tests and hack and modifications that we have been talking about. So overall guys, I believe that this converter is a good candidate for our innovative DIY MPPT solar battery charging project. And if you guys would like to see all the future videos and progress, don't forget to subscribe to the Innovation Lab. Also guys, if you enjoy DIY projects and you like to build things for yourself, so I built this constant current and constant voltage DC to DC buck converter, and I made a video to show you guys how you can do this from scratch. I provided all the schematic. So if this is is something that sounds interesting to you, you can go check out this next video. All right, my friends, I'll see you guys in the next one.